Yeah. So, okay, as I was saying, that we are going to use three components, which as part mean there is no any internal source of energy. So we are going to consider resistor, capacitor, and inductor in the electrical modeling, on the modeling of electrical circuit. So as you can see, we are going to summarize the relationship between the voltage and current and the voltage and charge of those components. And we consider all the initial condition equal to 0. So as I show you this, we have, as I can show you this one, so we have the resistor, we have the capacitor, and we have the inductor. So as I can show you, we have different relationship. This is first what we call the voltage current relationship. So we are trying now to find the voltage, uh, that is applied to the capacitor. This is the formula, which is 1 over C integral of 1 to 0. So you can remove the boundary. You can just remove the boundary. Let's keep it, remove the boundary. Okay. You can remove the boundary. So it's going to be 1 over C integral of I T. So this is I T, yeah? Is not tau. You could take it as the time. And yeah, take it as the time. So okay, good. I think okay. So get as the time. Then we have also the for the resistor, which is ohm laws. So all of you know that this law is like the first thing that you must know when you are in electrical engineering. So it's simple to know. And also this is the formula for the capacitor. And all these relationships are given to us. They are in time domain. They're in time domain. Remember when we solved the transfer frequency domain. So we found it in frequency domain, not in time domain. So, but this relationship are given to us in time domain. So that means when you want to solve a problem in of electrical circuit, you can really find. You can write your physical law in frequency domain, but remember to solve them in frequency domain. So you have first to apply the Laplace transform on all these formulas. So you have to apply the Laplace transform of, but before you apply the Laplace transform, you have first to get the model. After you get the model, then you can apply. But as we are moving, we can see how we can bypass that that part of applying the Laplace transform, so we can go straight to we can solve them straight in frequency domain. You're gonna see the law of impedance. So this is giving us just the relationship of current voltage. So now that one, it was for voltage. Current now is current voltage. When we want to find the current having the voltage, this is how you can solve your problem. This is how you can solve your problem. So I think this is how you can solve your problem for the capacitor, for the resistor, and for everything that we have. So yeah, guys, give me just a minute. Okay. So now can share my screen. Let me. Okay. Let me just try to log out here. Okay. Okay, guys, can you hear me? Hello, guys, can you hear me? Yes, sir.
Yeah.
Okay, guys, can you hear me? Okay. Hello, guys. Can you hear me?
Yes, sir.
Okay.
Yeah.
Yes, sir. Okay.
Yeah, now I'm using my laptop. Okay. So, uh, as you can see, we have these different components. We have the voltage current, the current voltage, and we have also what we call the voltage charge. But this one we are not going to use it, I think, in this year. But it's also important for you to know them. And we have also the impedance law. So the impedance law, I'm going to explain it later so you can understand how we find this value. So this is just like a frequency. So let us now try to go to this first example. So this is going to help us now to understand better what we are doing here. So let me try to go back there. And let's go back there. So it is this meeting here. Let's see. Okay. Whiteboards. Okay. Whiteboard here. Okay, we have our whiteboards. So we have the problem which was given to us. So which is okay, it's still coming on. Let's wait for it. Okay. So this is the problem which is given to us. They say find the transfer function relating the capacitor voltage V C of t to the input voltage V of t. So they've already specified for us the output and the input. So it happened that when you are solving this kind of circuit, the first thing that you have, if they gave you the problem like this without specifying what is the input and the output, the first things you need to do is to determine what is the input and what is the output before you start solving this problem. So that is very important for you to be able to find the transfer function. So in this circuit, we can choose anything to be a input or output. We can say, okay, our output is the current and the input is the voltage. Or you can say, okay, our output is the inductor voltage and our output is inductor voltage, and you use the VT, which is the input. Or R can be your output, or you can use the voltage between R and L and R as a input. So depend on whatever you're gonna choose and whatever they're gonna ask you to find. So that's why they say several variable could have been chosen to be the output. For instance, the inductor, the voltage, the capacitor voltage, the resistor voltage, or the current. You can even choose, say, okay, I will choose the resistor and the capacitor voltage to be my output. You can still doing that. Or you can say the inductor and the capacitor to be my output. So whatever you can choose depend on you. But in this particular problem, we have already the input and we have already the output. So they say the input is VT and the output is VCT. So we have to find the output. So our transfer function, that means they're asking us to find the transfer function, which is going to be, so okay, let's go. Okay. Okay, so the transfer function is going to be, so what you're looking for is going to be G of S, the transfer function. This must be equal to, let's do V C of T over V over V of T. Okay, so this is what they're asking us to solve. So the problem given to us is, let me try to draw it. So we have the inductor, then we have the resistor, then after that, we have the capacitor, and we can also go there. Okay, we have our input voltage, which is V of T, and there we have VC of T, the output. There we have R, there we have L, then here we have C. Okay, and inside here we have the current flowing there, which is I, we in time domain, I of T. Okay, so they're asking you now to find, the output voltage. So the first thing what we need to do is we have to identify different components that we have. Then we can write their physical law in order to get a mathematical model. So let's go back to our table that's going to help us now to determine what we need. So we have this table here. Okay. So we have the capacitor, we have the resistor. So we know that the voltage resistor. So let me go first back to this one, and let's go back to that one. And okay. So if we consider just this circuit here, we need to write a like a Kirchhoff law, which relate the voltage. So the current voltage, the voltage current. So we can say, okay, this one gonna be V of T is equal to what? According to the Kirchhoff law. So it's gonna be the sum of voltage. So we're gonna have V of L T plus VR of T plus what? VC of T. Because we know that the current flowing in this circuit is the same current, but the voltage will be the sum of different voltage. So this is what we can write as a Kirchhoff law for this circuit here. So, and now we can now try to determine the voltage of each different component here. So let's go back now to see what is the relationship between the current and the voltage of these components. So we can now go back. So what we have is, for the capacitor, we know that the voltage gonna be what? Guys, are we there? Are you there, guys?
Yes, sir.
So you are there, guys? Okay.
Yes.
Okay. Okay. So let's go now. Here. Oh, where is it? Okay. Sorry. I want to go here. Okay. So now we can write our equations. Are we together?
Yes,
So
sir.
we can write our equations, which gonna be VC. Okay. Let's write it even here down. We can write it on the same side there. VC of T will be equal to what? We know that from the table, okay, from the table, the inductor voltage is L times di of t over dt. So that's why we're gonna have here. So we're gonna have there, we're gonna have let's say L, the inductor L times what? D I of t over dt. Okay. Plus the resistor voltage is going to be R times I, small I of t. Then plus, let's go in the table, we can see it's going to be, I think, 1 over C integral of I of t. Are we together? Okay.
Yes, sir.
So now this is our equation, which gonna be V of t, which is equal to L di of di dt, okay, plus I of t there, plus R. Let me write it properly so you can see properly. Okay. Okay. So it's L. It's L di t over dt plus R I t plus 1 over C integral of I of t. Okay, so this is basically what we have. So this one is the input equation. So we want now to find also the physical relation of the output, right? So this one we can express this in terms of, depends, you can express this in terms of voltage or in terms of current. Let's try to express this in terms of current. So let's see the relationship between these two in terms of current. So it's equal to IT is equal to C dV dt over dt. Okay. Okay. So we're gonna have, so this is gonna be, when we want to write the current for going there, it's gonna be I C, no, I of t, because it's the same thing. It's going to equal to d v c of t over okay, over dt times c. Okay, times c. So this is the formula here now. So after we got these two relationships, so we can call this one can be 1 and this one can be 2. So having these two relationships now, we can now try to apply the inverse Laplace transform to these two system of equations. So it's like we have a system of equations. So when we apply Laplace transform there, it's going to give us, it's going to be V of S, which is going to be equal to L times S, because this one is going to give us S, E of S plus, this is the Laplace of derivative, that's why there is S there. Eh? Are we together, guys? Okay. So then Gonna do now plus R I of S, then plus, so the Laplace of integral is gonna be 1 over C times S I of S. Then down there, when we have this gonna be I of S is going to be equal to what? Going to be equal to this one gonna be VC of S times what? Times C
MC.
S. Or you can just write it, say, for you to be able to see, you can just say it's gonna be okay. Gonna be S. Okay, it's the same thing, right? So from here, you can call this one is 3, and that one is 4. Good. So from here, you can be able to see that we have our 4 equations there, and having those 4 equations, this can help us now. This can help us now to so we have, let's say we have 2 equations because now we are in frequency domain. So in that way, we can even be able now to solve this system of equation. We have a system of 2 equations where we can find E in the 2 equations. So we can replace the value of E in the first equation, then we can be able to solve it. So this now can be now solved. Let's now, can I wipe, guys? Can I wipe this?
Yes, sir, you can, sir.
Okay. So let's go there. Let's go there now. What are you going to have here? We're gonna have something like let's see, we're gonna have something like okay, V S will be equal to L. Okay, so we can replace here L times what? Times what, guy? Times CS, right? Are we together? Are we together, guys?
Say,
Yes, yes, sir.
Okay. Yes.
did you record the class?
Yes, I'm recording it already. Yeah.
Say, our timetable says you have a class with us on 2 to 3.
2 to 3.
Yes.
No, there is no such class. There is. I have a class from 2 to 4.
Yes.
Yeah, I have 2 classes today. One in the morning and one in the evening, in the afternoon.
Say there was a load shedding. That's why. Didn't ask this.
Okay. Yeah, I'm recording. So yeah. Oh, I know. Yeah. So let's now go plus R. Is it V? Let me just try to do it like this. Oh, okay. What is the value of the current there? Let's replace now the current also there. So this is gonna be R times what? This current, the current is times R times the current, which is equal to CS VC of S. Let's go now. Plus 1 over CS times what? Times CS VC of S. Okay. Okay. So this one can simplify that one. Okay. Then here we're gonna have now. So we have V there, and V there. So we can put it like this. VS. Remember, this is the input, and this is the output. So we're gonna have now LCS square plus RCS plus 1, and we put it together. So we're gonna have V C of S. So what we wanted to find now is this one over this one. So we can do the cross multiplying. So this is gonna give us now, we're gonna have VC of S over V of S is going to be equal to what? 1 over LCS square plus RCS plus 1. Here is now we have find our G of S, which is the transfer function of this electrical circuit when the capacitor voltage is the output. So guys, is there any question? Guys, before we move on, is there any question?
No
No.
questions, sir.
So everything is clear?
Yes, sir.
Okay, thank you very much. Yeah, thank you very much. So we can now try to move on. So now, as I told you, that when you have a problem, you have first to find the relationship in frequency domain, first the relationship in time domain, then you can convert it in frequency domain. Now I want to show you something that can help you to get right of the time domain, so you can go straight to the frequency domain. So let me first put this one back. It was V of T, and there was a small C there. Okay, so what we are going to do now is what we going to use a technique that's going to simplify the solution. Instead of going to all those long process here, so we are going to see a simple process which gonna help us to find a solution. Let's say when we have, let me just take a simple example. When we have the inductor voltage, it's given to us is L dt di L di of T over dt. So this is given to us in time domain. Once we convert it in frequency domain, this is gonna be L S. That's all. Is it right? Times what? Times I of S. And the capacitor, which is 1 over C integral of I of T is going to be 1 over CS times IS. So, and the resistor is going to be only RIS. So we all know from electrical edge that the voltage let's say in the resistor or whatever, it's equal. When you talk about the voltage is equal to V, let's say VL is equal to Z times the current. Are we together, guys? Guys, are we together?
Yes, sir.
Yeah, so ZL times the current. So now from this one, we can call, because we have here the currents. So this one can be called our impedance, right? So this LS will be the impedance, and this one the impedance of the inductor, and you can call this one over C the impedance of the capacitor, and this R is called the impedance of the resistor. So following the impedance law, it's gonna now be easy for us to solve this problem. So because we're gonna have here now, we can now have this one and say, when we have our problem in let's say VT is equal to VL plus VR plus VC, or we know that this one is our VL, and that one is VC, and that one is VR. So we can easily write in terms of because when you apply Laplace, so this one is in time domain. Sorry, time domain, and there time domain. So if we apply the Laplace, we're gonna have Vs is equal to VL S plus VR S plus VC S, which gonna be that one also. There is S there, there is S there, and there is also S there. So guys, you can see now we have created from the impedance law, we can simplify our model. So now instead of you trying to solve your problem in frequency domain, we can redraw our circuits, which gonna be there, and knowing like okay, is now and there. So we're gonna go down there, and there we're gonna go, and we have this. Okay, this is V. Now it can be VS is the input. There we're gonna have LS, and then we're gonna have R, and here we're gonna have 1 over CS. Then the current flowing here is going to be IS. Are we together?
Yes, sir.
Guys, are we together? Yeah. So now following this impedance law, we can now start using our system in a frequency domain instead of solving it now in a time domain first. So when they give you a problem, now to solve it, it becomes much easier. So let me delete this one. So let me where the mouse. Okay. Let me just clean all this one. So let's go to this same problem that was given to us. They say, find the transfer function relating the capacitor voltage and to the input voltage V of t. So you can just draw your circuit and say, considering the impedance law, you can draw it now, considering the impedance law, which is give you this one. So for considering the impedance law, what we have is something like the resistor, then we have the capacitor, and you can go there. Okay, so this one gonna be already V of S, and this one L times S, that one will be R, and this one over CS, this is the current. So I S. So when we have now to write these things straight, so you can write the equation that we have before. It's gonna be like we write, say the V of S, the voltage is going to be now equal to what? L S plus R plus 1 over CS. Everything's times I S. Are we together? Then you can say, okay, the capacitor voltage C of S is equal to what? Is equal to 1. You can say is equal to 1 over CS times, let me write this one, times, okay, times I S. So this make your problem easy. So writing that, you can write, say, V C of S, the transfer function G of S. Yeah. Okay. Okay. Transfer function G of S is equal to over V of S. So it's going to be easy. Then we have your 1 over CS times EIS over LS plus R plus 1 over CS times IS. You can simplify this one, that one. So this one can be now G of S is equal to VC of S over V of S, which is going to be now simple. So you can still solve this one. Is this one gonna give us? Can give you all 1 over. When you find the LCD here, it's gonna be LCS square plus RCS plus 1. So you see, then this is gonna be over CS, and they're gonna be over CS. So you can simplify this CS. So you have already your 1 over LC square plus RCS plus 1. Guys, are we together? So you can just see here you have solved the problem in very, very simple step. So you can just use 1, 2 lines, and everything is solved for you. Okay, guys? Are we together, guys?
Yes, sir. We are still together, sir.
Yeah, okay. So next time, if they give you this kind of problem and they ask you to find the transfer function, you don't have to go through all those time domain, apply Laplace. So you can use straight the impedance law, unless if they say find first the solution in time domain. Then you can find in time domain, then you can apply Laplace, then you can also solve it in a frequency domain. So this is basically what we are going to do with electrical circuits. So you can see this is it was a one loop problem. So we're going to see now a two loops problem. So this is gonna also be useful for us. And let me just try to go here. Mhm. Okay, so let's see what you can do now. Okay, we have now this problem, we have solved it. Okay, now let's go to the problem with two loops. Okay, so we have one loop and two loops. So they say, referring to the circuit below, use mesh analysis. So you know how to use mesh analysis with transfer function impedance to get the transfer function G1 I1 over S and G2 I2 over the current of the second loop over S. So, but we are going just to solve for this one for G2. So we're going to solve. So let now try to draw this one. Let's see, R and L, R and capacity. So okay, let's put it now there. So let's try to solve it to draw it. So we have resistor, then we have here, then go back. We have our voltage, the input voltage, V, you can write already V of S, and this is going to be R, this is going to be LS. So let's go there, this can be R1, going to be R2, then we have this capacitor, okay, this is 1 over CS, okay. So we have I2 inside here, I2, and we have I1 there. So, okay, guys, let's move together. So you all know how to use Kirchhoff law or mesh law. So we have the first mesh and the second one. So writing the equation, we will have the input Vs will be equal to what? For let's consider only the first loop. So we're gonna have Vs, the input is going to be equal to let's say RIS, is it? Okay. Okay. RIS plus L. Here we're gonna have what? This is what I1, right? Because this current. Gonna have I1 S minus what? Because the I2 also is flowing in this one, but it's gonna be in a different direction. It's gonna be L I2 S. So this is gonna be LS. Oh, and there is also LS. Okay. So this is for this first loop. For the second loop, then we're gonna have this one LS. Now we can write it LSI 2 S plus R2 R2 I2 S. Then we're gonna have plus this one 1 over CS I2 S. Then we're gonna have minus, because there is another current flowing here, coming from L1, this is gonna be LS I1 S. Are we guys together? Guys, are we together?
Sorry, sir. Can you please repeat loop 1, sir?
Loop 1. Okay.
Yes, sir.
So, you know, in loop 1, we have current I1, right? Which is flowing here. So, for this loop 1, so we'll have our voltage will be the voltage flowing in this one plus the voltage which is flowing in that one, right? Are we together?
Yes, sir.
Hello? Yeah.
Yes.
But because in this one we only have two currents flowing in this one. So we'll have two voltages here, right? The voltage from I2 and LS and the voltage from I1 and LS. Because we are considering this one, taking in account the direction of the voltage, so this voltage here will be this voltage here minus the voltage on this side. Are we together?
Yes, sir.
Yes, that's what I take this R. This is the voltage flowing the resistor. Then I do plus this voltage here times this coming from this side. I1 times this one is the voltage there. This voltage. Then I use again, I subtract the voltage that are coming from the current I2 flowing in the same circuit. If let's say we had this arrow in this direction, I add this voltage instead of subtract. I think you know that, right?
Yes, sir.
Yeah. So this is what we have here. That's why I say here, this is S. Sorry, this one is S. If you don't see it properly, it's S. Okay. Let me write
Okay.
it properly. Okay. So LS. Yes, these things of writing. Okay. So we have this one now. We can group it. Then we can have, let's say, R1. This is R1. Sorry, R1 plus L S I1 S minus LS I2 S, which is equal to VS. And this one is going to be equal to what? To 0. Okay. So the second one we're gonna have is going to be, let's say, R2 plus LS plus 1 over CS I2 minus L. No, this is not like that. This is LS, not L. This is LS. This two is also LS. So is LS times I1 S is equal to 0. Okay. From here, you can apply any other methods to solve your problem, to find I1, I2, but we prefer here to use Cramer because Cramer is quite easy for us to solve in when we have something like this. It's quite like many times you can just make it in a simple way. So the Cramer method, we know that the first thing to find is gonna be a delta. Let's try to solve finding delta. Okay, guys, I think I can stop by here. We're gonna continue at past 2, because even if I start now, I can't finish. So we're gonna continue at past 2. Sorry for those they had load shedding. At least the class is recorded, so they can have time now to they can have time to catch up this class here. So